So let's start off our journey into floating point multiplication by looking at an equivalent example in decimal. So let's say we wanted to multiply together 5 times 10 to the power of 2 with 3 times 10 to the power of 3. So we can think about this 5 times 10 to the 2 as our value x, and our 3 times 10 to the 3 as a value of y, and we want to multiply x and y. So 5 times 10 to the 2 is the same as 5 times 100. 3 times 10 to the 3 is the same as 3 times 1000. So 5 times 100 is 500, and 3 times 1000 is 3000. So when we multiply these two numbers together, we're going to multiply the 5 and the 3, which will give us 15. And then we're going to be left with 1, 2, 3, 4, 5 nothings. And this is the 5 nothings we have here. So this again can be written in scientific format as 15 times 10 to the power of 5. So we just go from the decimal point here and we count in 1, 2, 3, 4, 5 to get to this point here. So the answer to multiplying these two numbers together is this number here. So how did we get to this number? Well, we got to this number by multiplying the 5 and the 3 and adding the 2 and the 3 to give us the value of 5. So if we were to think about this number 5 and the number 3 as being equivalent to the Mantissas, then we get the multiplication by multiplying the Mantissa together to get 15. And these two numbers are our exponents, so we get our final exponent value by adding the exponents. So we're going to be left with our 15 times 10 to the power of 5. Now if we were to normalise that, we would write that out as 1.5 times 10 to the power of 6. So if we look at this mathematically, we could say that x times y is going to be the multiplication of the Mantissa of x with the Mantissa of y times 10 to the power of, and then we add the exponent, so it's the exponent of x plus the exponent of y. Now we know that we're not using the base 10, we are using the base 2, or equivalent we could call it the radix. So we're using the radix 2, so we can write that x times y is the multiplication of the Mantissas times 2 to the power of the addition of the exponents. So that's relatively straightforward. If we want to multiply two numbers, we multiply the Mantissa and we add the exponent. But what's going to happen to the sign value? Well, we know that whenever we multiply together a positive number with a positive number, we get a positive number. When we multiply a positive with a negative, we'll get a negative. Equivalently, a negative with a positive will give us a negative. And if we multiply together two negative numbers, we get a positive number. So that's just basic arithmetic. So we know in our floating point number system that a positive number is given by the number 0 and a negative number is given by the number 1. So we can just replace the plus and the minuses here with a little truth table. So the plus and plus equals a plus would be 0 times 0 would give us a 0, and we would have a 0 times 1 would give us a 1, 1 times 0 would give us a 1, and 1 times 1 would give us a 0. So if we have a little look at this, you may recognise this as the truth table for an exclusive OR gate, and I've got the exclusive OR gate drawn here. So in order to work out the sign value, we simply have to take the sign for the x value and the sign with the y value and exclusive OR them, and we'll get the sign of the output which has been multiplied. So this is the basic idea of multiplying together our floating point numbers. We exclusive OR the signs, we multiply the Mantissas, and we add the exponents. It's really that simple. So let's go ahead and we'll look at an example. So we're going to work through our first multiplication in detail, but I do have an automated tool which we will see nearer the end of the video, which automates the full process for us, but it's good to work through the very first one by ourselves. So we'll have to pick two numbers to multiply, and I've picked two numbers pretty much at random. So the first number that we're going to multiply together is going to be minus 0.7. So this is minus 0.7 here, and it's written in our 32-bit floating point binary as this number here. And you can see that the 32-bit floating point binary number gives us an approximation to minus 0.7. We don't get exactly minus 0.7. So we're going to take this number here, and we're also going to multiply this number with our second number. And this is our second number here, 492.75. Now you can see here that we've got an exact representation of this 492.75, and this is the 32-bit number we have here, and you can see how it's generated below. So let's go and have a look at the answer. So when we multiply these two numbers together, we're going to get this 32-bit floating point number here, which gives us this number in decimal, and this is how it's calculated. So I've gone ahead previously and worked this value out for us. So we have the two numbers that we're going to multiply together, and we have our final answer to make a comparison and just to check. So let's go ahead and we'll go through this full multiplication using those two numbers. So I've rewritten the two numbers here. We have our minus 0.7 and we have our 492.75, and we have them here in the 32-bit single precision floating point format. So we want to multiply these two together. Now we know in order to multiply them, we have to multiply the Mantissa's, add the exponent, and we also have to do an exclusive OR on the sign. So let's tackle the sign bit first. So the sign bit's relatively straightforward. We're looking at this and we're saying a positive number times a negative number. Well, a positive number times a negative number is going to give you a negative number, so you're going to end up with a value of 1 for the sign. So we can put a 1 here for the sign. So that's us worked out one of the 32 bits that we need to work out. So let's go ahead now and we'll look at the exponent. So we said that what we have to do is we have to add the exponent values. So we have the exponent value here for the x, okay, so this is the top one, and it's going to be a value of, well, we start from this point here, so there's 1, 2, 3, 4, 5, 6, 7, 8 bits. So that's going to be a value of 2 plus 4 plus 8 plus 16 plus 32 plus 64. When we add all those together, we're going to get the value of 126. So the exponent value that we have here is 126. But we have to take away the bias. So if we take away the bias, we're going to get a value of minus 1. Now we do the same for the y value. So the y value is going to be these 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. Now whenever we add these together, we're going to get the 1 plus 2 plus 4 plus, and this would be 8, 16, 32, 64, that would be 128. So it would be, finally when we added the numbers together, we're going to get a value of 135. And again, whenever we take away the bias, we'll get a value of 8. So in order to get the value that we're looking for, we then have to add the minus 1 and the 8. So minus 1 plus 8 is a value of 7. So the exponent we're looking for is a value of 7. So in effect we have 2 to the power of 7. But that's not the complete story, because this exponent value may have to be changed, and we'll see that whenever we go ahead now and look at the multiplication. So again, I've written the two numbers down here. We have the top number here is our minus 0.7 and the bottom number here is our 492.75. So we're interested in multiplying together the Mantissas. So what we can do is we make a note here of the beginning of the Mantissa. So this is the sign, and then we have the 8 bits for the exponent, and the Mantissa starts from here. So from this point along to here, we have our 23 bits. And again with the second value from here along, we have the 23 bits. So what we're going to do is we take these 23 bits, and I've rewritten them down below, and you can see from this point here, we have our 0, 1, 1, 0, 0, that's our 0, 1, 1, 0, 0. So from this point here along, we have our 23 bits. And the same for the bottom value. From this point here with the 3 ones, 0, 1, 1, and you can see the 3 ones, 0, 1, 1, and we have the rest of the bits. So that's 23 bits to here. Now there's one added complication here, and it's that whenever we write out our normalized number, we make the assumption that it actually has a value of 1 in the front of it. But we don't actually see this one. This is a hidden bit. We don't actually need to write it down. We assume it's a value of 1 because it's normalized. But in order to work through the multiplication process, we have to take this into consideration. So what we do is we append or we add on that 24th bit. So we've added on the value of 1 and a value of 1 here. So now what we're actually multiplying together are two 24-bit numbers, and this is the 24-bit number here. So the 23-bit plus the 1 and the 23-bit plus the 1. Now whenever you multiply together two 24-bit numbers, you're going to get a 48-bit number. And that's the same as saying whenever you're multiplying together, say the value 5 and the value of 10, you're going to get a value of 50. So you've got a 1-bit number, and a 1-bit number will give you a 2-bit number, so you're just going to be doubling the numbers. So we've got a 48-bit number here in the bottom line, which is the multiplication of these two numbers. So I've drawn out the actual multiplication table here. So we take the 0 here and we multiply it by everything we have here, and it would just give you a value of 0. And then you would shift in to the left by 1, and you would multiply the next value 0 here with everything else, and again you get 0, and you would shift in. But I haven't actually drawn all those zeros in, so all we're going to have then is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros. So I have the 13 zeros here, and the very first one that multiplies is this 1. So we'll say 1 times all of this just gives us all of this, and then we shift 1 to the left and we go 1 times all of this gives us all of this again, and we shift 1 to the left and we've got the 0 again, and we continue on in that process, and you create this multiplication tree. And then finally what you do is you have to add the values. So we're going to have 1 here, and we're going to have 1 plus 1. So 1 plus 1 will give us a 0, and you would carry 1 into the next value. And we would have 1 plus 1 again, we give the 0, we carry 1 into the next value. So we would add in all of these values, and when we've added all the values in, we would have this 46-bit number that we see here. But we have to ensure that the final answer is normalized. That is, it has to start with a value of 1. Now if we look at this here and we say, where is the decimal point in this number? Well, the decimal point is going to be given by 23 bits here plus the 23 bits here, so it's going to be 46 bits in. So we count along 46 bits, and the 46 bits is this point here. So we've got a total of 48 bits, and there's 2 of them are going to be at the left of the decimal point, and the other 46 are going to be at the right of the decimal point. So if the decimal point is here, and we've said that we normalise this by ensuring that the highest bit is a value of 1. So the highest bit here, a value of 1, is this bit here. So that means that the decimal point is going to have to move from here, and it's going to have to move to the left by 1 position in order to normalise the result. But we know we're going to have this value here, and it's going to be times the exponent value. Well, the exponent value worked out in the previous page was 2 to the power of 7. But now that we've taken this decimal point and we've shifted it to the left by 1, well, this number here is going to be the same as the number below, with the decimal point shifted 1 to the left, and the exponent now increased to 2 to the power of 8. So we're just saying that this number here is the same as the number above. It's just been normalised, and by normalising it we change the exponent value. So let's finally have a look at the final output of the sine, the exponent and the mantissa. So I've rewritten our final number up here, and this is our 48-bit number, and it's times 2 to the power of 8, and there's a appended by a value of 1, and that's the decimal point. So we know that the sine is going to be a value of 1, we talked about that at the beginning, and the exponent is now a value of 8. So to get the final exponent value, we have to add the value of 127 back on. So we add 127 back on, we get the value of 135, and this here is the final exponent value. Now the Mantissa value is going to be the first 23 bits after the decimal point. So the Mantissa value is going to start 01011. So you can see here 01011, and we're going to count along the 23 bits. Now there's actually going to be some rounding as well. So we need to look at the remaining 23 bits in order to work out a rounding value, but we'll get into that detail in a later video. This is our very first multiplication, and it takes a little bit of time, but just take your time to read over it and think about it. But we've also got an automated process, and we're going to learn a lot from looking at the automated tool, so we'll get onto that in the next video. So thank you for listening. I'll get you on the next video. Goodbye.